Recognizing his momentous commitments to the discipline of material science, Kaku has gotten significant acknowledgement for his emphasis on the momentous potential opened by the James Webb Space Telescope, JWST. This phenomenal instrument has accomplished critical achievements, counting the disclosure of 6 huge worlds that challenge previously held logical convictions. These worlds were once thought about inaccessible by current research techniques, yet their revelation offers an unprecedented opportunity to upgrade how we might interpret the universe. What makes these revelations particularly compelling is their evident straightforwardness, yet they discreetly push the limits of laid-out hypotheses concerning the development and advancement of universes. It is critical to examine these disclosures intently as they stress the critical job that logical progression plays in forming our impression of the universe. Kaku, an exceptionally regarded figure inside the academic local area, is generally respected for his extensive knowledge of both old-style physical science and quantum mechanics. His unique background, which bridges both American and Japanese cultures, has fueled his strong passion for investigating the novel possibilities disclosed by the JWST. He enthusiastically embraces the telescope's discoveries, energetically sharing them with the general public, highlighting his dedication to broadening humankind's appreciation of the universe. His openness to engaging with these new revelations, which can no longer be excused, mirrors his obligation to advancing human knowledge. Kaku's unmistakable perspective radiates through in his reflections on the JWST's disclosures, which have reignited his scholarly interest. Throughout his career, Kaku has been known for his openness to offbeat ideas, welcoming concepts that challenge long-established principles. While he recognizes the significance of Einstein's theory of relativity and Newton's laws in contemporary science, he argues that these theories do not fully explain the universe's complexity. Kaku contends that the JWST discoveries may significantly change the field of cosmology. Although many of his colleagues remain skeptical of this viewpoint, such wariness has led to doubts and criticisms, particularly from advocates of the Big Bang theory and quantum mechanics. Nonetheless, Kaku stands firm in his conviction that the JWST has revealed 6 colossal universes dating back to the early universe, each containing a larger number of stars than our Milky Way. These worlds formed just 200 to 700 million years after the Big Bang. A group of cosmologists has fittingly named these surprising cosmic systems universe breakers because their revelation challenges current cosmological models. If these discoveries are validated, they could dramatically reshape our comprehension of the early universe, suggesting that its initial stages were far more dynamic and complex than previously believed. The dominant hypothesis regarding the universe's origin asserts that after the Big Bang, the universe was chaotic, and it took a long time for the first solid structures to emerge. It was once assumed that galaxies began forming much later. However, the massive universes identified by the JWST are already larger than the Milky Way. Furthermore, their extraordinary brightness indicates that they may have been producing stars at a much faster rate than our own galaxy. In contrast, the Milky Way generates stars at a slower, more unpredictable pace. While the exact timeline for the development of the first cosmic structures remains uncertain, it is certain that the early universe may have started with isolated stars or small clusters of stars that eventually merged into larger systems. For a long time, it was believed that such massive, evolved universes could not have existed so early after the Big Bang. This raises a major question. Is the universe older than previously thought, or did these gigantic worlds form much earlier than anticipated? This idea presents a significant challenge to conventional scientific understanding, which still struggles to reconcile these new discoveries with existing models. Some physicists have even dismissed these findings, questioning the accuracy of age estimates. However, Kaku is fully aware of these criticisms and has openly expressed his stance on the matter. He points out that many outdated theories persist due to the influence of prominent scientists, despite being disproven by later research. Kaku insists that genuine scientific progress comes from empirical researchers who focus on precise and accurate theories. He further emphasizes that humankind's understanding of the universe's origins remains incomplete, highlighting the need for continuous testing, revision, and refinement within the scientific process. The concept of the universe's origins was first introduced in 1927 when researchers discovered that the universe is expanding, suggesting that it originated from an infinitely dense point and has been expanding ever since. At the time, the idea of a universe with both a beginning and an end seemed unimaginable to many. Even today, science still struggles to fully embrace this concept. Regardless, it is essential to remain open to such possibilities, even when new discoveries challenge long-held scientific beliefs. History has demonstrated that scientific knowledge is always subject to revision. For example, in Einstein's youth, it was widely accepted that stars and planets held fixed positions in space. Today, we know that everything in the universe is in motion. Planets orbit stars, stars travel through galaxies at immense speeds, and entire galaxies drift through space with their ultimate fate uncertain. This realization has overturned centuries-old beliefs and reinforces the necessity of continuous scientific inquiry and adaptation. Today, scientists must embrace anomalies and recognize that theories are never entirely complete until they are thoroughly tested and validated with observational data. The Big Bang theory, for instance, emerged from observations that galaxies are moving away from us, with the distance between them being proportional to their separation from Earth. This theory, known as Hubble's law, was further supported by evidence such as cosmic microwave background radiation and the redshift of distant galaxies. However, it is crucial to remember that there was a time when people believed the Earth was flat and that the Sun revolved around it. These ideas were based on the best available evidence of their era. Technological advancements have since revolutionized our understanding of the universe, and we now find ourselves in a similar situation as new data from the JWST challenges some of our past assumptions. This situation exemplifies the ever-evolving nature of science, where experts must remain open to new findings while re-evaluating established theories in light of emerging evidence. The unexpected discoveries from the JWST challenge are current cosmological understanding, prompting a reassessment of long-held models. Science heavily relies on redshift measurements to determine the distance and velocity of celestial objects. Redshift refers to the change in light's color as the source and observer move relative to one another. For example, when a distant light source, such as a star, moves away from us, its light shifts toward the red end of the spectrum. Conversely, when it approaches, the light shifts toward the blue end. This phenomenon provides fundamental data on the movement and distance of galaxies. However, even minor errors in redshift measurements can lead to significant consequences. As a result, many traditional assessment methods are now under scrutiny due to the new revelations made by the JWST. These recent findings urge scientists to reconsider whether these results could be attributed to errors in redshift measurements or if some researchers are overlooking current data. This issue requires careful investigation and thorough review of both the data and the methods used. Continuous evaluation is crucial, reflecting the growing recognition within the scientific community that relentless inquiry is essential to advancing our understanding of the universe. The discovery of these immense galaxies has profound implications for cosmology, prompting scientists to rethink and refine existing models to better explain the complexity and diversity of galaxies observed across vast timescales. These findings underscore the dynamic nature of scientific knowledge, where new discoveries spark further breakthroughs and open new avenues of research. As scientists continue to analyze data from the JWST and other observatories, the study of galaxy formation remains a rapidly evolving field. Each new discovery brings us closer to understanding the fundamental processes that shaped the cosmos and the universe as we know it today. The JWST's discoveries serve as a reminder that the scientific community must remain flexible, willing to question long-held beliefs, and adapt to new evidence. Scientific progress is driven by the willingness to revise outdated theories in response to new data, and the revelations made by the JWST exemplify how a single breakthrough can prompt a reassessment of the fundamental principles of our understanding. As we move forward, one thing is certain. The JWST has reignited our curiosity and opened new frontiers in the exploration of the universe. The JWST's ability to peer deeper into space than ever before has unveiled a wealth of unexpected phenomena, raising fundamental questions about the timeline of galaxy formation and the overall structure of the universe. Scientists are now grappling with the implications of these discoveries, as they challenge the very foundation of our understanding of cosmic evolution. One of the most astonishing revelations is the apparent maturity of these early galaxies. According to prevailing cosmological models, galaxies in the early universe should have been in their infancy, characterized by irregular shapes and relatively low stellar mass. However, the JWST has revealed galaxies that appear remarkably well-formed and massive, suggesting that galaxy formation may have occurred at an accelerated rate or through mechanisms not yet fully understood. This discovery has sparked debates among astrophysicists, some of whom propose that our models of dark matter and dark energy might need revision. Others argue that there could be alternative explanations, such as observational biases or unknown astrophysical processes that facilitated rapid star formation and galaxy assembly. Furthermore, the JWST has provided unprecedented insights into the chemical composition of these ancient galaxies. The presence of heavy elements, which are typically produced in the later stages of stellar evolution, suggests that star formation and supernova activity were occurring at a much earlier epoch than previously anticipated. This finding has profound implications for our understanding of nucleosynthesis and the enrichment of the intergalactic medium. Another intriguing aspect of these findings is the potential reconsideration of the cosmic expansion rate. Current models rely heavily on the standard cosmological parameters, including the Hubble constant, which describes the rate at which the universe is expanding. If these early galaxies are indeed as massive and evolved as they appear, it may necessitate a reevaluation of our measurements of cosmic distances and expansion history. Some theorists even suggest that our interpretation of redshift, the key method for determining the age and distance of celestial objects, may need refinement.